Hey there, team. You ready for video number 9 in our wonderful journey through the valley of the shadow of electrochemistry? We'll get out sooner or later. This is a rough chapter for some people, and some people love it. It just all depends, right? Some people like organic chemistry, some don't. Whatever. This chemistry is so broad. There's something for everybody, which is wonderful about it. All right, we've learned already about cell potentials, only at standard conditions though. We haven't done non-standard conditions, and how to calculate those using our reduction tables, right? Finding out what's the anode, what's the cathode. You know, we got to reverse the anode equation because it's the opposite of this. So if we reverse this, we change the sign and then add those two together and we're off to the races. And if E naught cell's positive, it's spontaneous in the direction written. If it's negative, it's non-spontaneous in the direction written under standard conditions. Pretty straightforward. Not like delta G, just opposite in sign. What I want to do is take this to a very specific application that's a whole lot of fun. This is going to be called a metal activity series, but one of the funnest things that I like to do goofing around, of course safely, is dropping metals in acid. I love watching the bubbles form and collecting those bubbles and putting them next to a flame. Make sure you do this under proper supervision. So metals can react with acids. It's a whole lot of fun. As long as their cell potential overall is positive, right? So if you take the anode plus the cathode, if that's positive, that metal will react. And a whole lot of metals do react, but some don't, which was, when I first did that, I thought that was surprising. A really fun demo is to take pennies, or cents technically. If you take a cent, I think prior to 1982, it was mostly copper with a little bit of zinc, like 95% copper, 5% zinc, something like that. But in post-1982, they swapped that and made it like 95-something% zinc with a little 5% copper coating on it. It's like those chocolate coins at Easter or something with the foil around it. So you open it up, eat the chocolate out, and you have the foil with nothing in it. What's really fun, if you take a file and go, I should have brought this with me. You file through until you just see a little bit of that silvery zinc metal underneath the copper coating. Pop it in some hydrochloric acid. And if we did it at 1 molar, this would be standard conditions. Anything other than 1 molar would not be standard conditions, of course, but it works. And then you start to see bubbles just emanating from inside of the penny, because the zinc reacts with the hydrochloric acid. The zinc is oxidizing and it's reducing the hydronium ions from the acid. But the copper didn't react. So in time, all the zinc reacts and you have this empty copper coating of a penny, and then it floats to the top. It's just like a shell, like you ate the chocolate out of the coin and you just have the foil on the outside. It's really fun. And if you're really on it, you collect the gas, because that gas is hydrogen gas. You take a test tube, fill it up with water, put a little paper towel on it, tip it upside down, catch the gas and displace the water out, and then bring that gas next to a flame. Whoo, hydrogen's flammable, yay! So the metal's oxidized to the cation, right? So that would be the anode, like aluminum going to aluminum +3 or zinc to zinc +2 or something. But some react and some don't. We're going to take a little shortcut and show you why. So this is kind of a fun application video. It's going to be a short one. The hydronium ion, or of course in electrochemistry, we're always using H+ as a shortcut. Just kind of nice. Because I drill everybody for hydronium, but now I'm like, but it's okay to use H+ for this one. That's going to be reduced because it's going to be picking up electrons. So the metal's losing electrons and oxidizing from a neutral solid to some cation. And then the hydrogen ions are going to pick up those electrons and reduce from a +1 to a 0, giving you hydrogen gas. And those are the bubbles you see. And that's why when you collect those, they make fun little noises by flame. That will be at our cathode. So if we just take the anode plus the cathode, boom, we got the overall cell value. So we can take any metal, right, oxidizing to some charge, and the anode, right, that individual electrode will be the opposite of the reduction. Remember, here, these are all reduction potentials for that electrode as a cathode. But if it's functioning as an anode, we got to reverse the equation, right? So for example, we take some of these metals here, right? This is the reduction, but we want the oxidation. So we want the metal, right, going to the cation, the metal going to the cation, which means we reverse this equation and we change those signs, all right? And then for the cathode, well, the reduction of H+, regardless of which way you go, that's going to be 0. That's our defined standard hydrogen electrode. So if we add those two together, the cathode's always going to be 0 because of the hydrogen reduction. And then the anode will be the negative sign of the value on here because it's functioning as an anode. We had to reverse it. So the overall cell potential will just be the negative of the value on this table. That allows us to do a pretty cool shortcut, because if the reduction potential is negative and you plug that value in and take the opposite of it, the overall cell potential will be positive. Oh, so what that means is any of these reverse reactions, for example, if I took lead or tin, right? These have negative values. So if I put lead or tin in acid, the lead would oxidize to +2, the tin would oxidize to +2, because you take those negative values right there, plug them in, the negative times the negative gives you a positive E cell. So any metal below hydrogen, below that zero line, all these metals, anything that's a solid metal, that'll oxidize in acid. Any metal up above it, oh no, so if we put these values in, these are all positive, right? So if you stick a positive value in there, that makes this term negative, and then the E cell would be negative, and it wouldn't be spontaneous. So these metals would, any metals you see here, you know, like silver and stuff, those would not react in acid. Copper is up here, would not react in acid. So you can really look at that and go, oh, copper is above. It has a positive reduction, which means it would be a negative E cell overall as an oxidation. It doesn't react, whereas zinc is below H+, it has a negative reduction potential. Stick that in there, it has a positive as far as oxidation. So zinc reacts with acid, but copper doesn't. Pretty weird. Let's do a quick little example here. We'll go ahead and do it the long way just so we get some more practice doing the half cells and stuff. But then I'll just show you how you could do it like on a test in like 5 seconds. You just read it off here. If it's a negative value, it works. Boom. All right, see if you can do this problem for me. Let's do it the long way, not the shortcut way. And then once we understand what's going on, we'll do it the shortcut way real quick. It's great for like some multiple choice. I'm not a big fan of multiple choice questions, but this would make a good multiple choice question. If I could like list 5 different metals and say which of these would react under standard conditions with hydrochloric acid. Well, I just look up the ones with negative values here and you're good to go. But let's take some aluminum. Well, let's try to predict ahead of time whether aluminum will react with hydrochloric acid. Now, understanding hydrochloric acid is a strong acid, it's going to ionize 100% into hydronium ions, which we'll be using H+ in this case, and chloride ions. Now, if you get a little more complicated, you have to worry about the chloride ions also reacting. Don't worry about that in this particular class. Let's do the 2 half reactions. So the metal's going to be oxidizing. So we got aluminum solid. So you should know by now aluminum's a type 1 metal, always goes to +3. So that goes to a +3 electrons. Righto, daddy-o. And then, of course, the hydrogen ions will be reducing. These will all be at 1 molar under standard conditions. And that goes to H2 gas. But we need 2 hydrogens, and then we got to double the electrons. Right on. So that's your standard hydrogen electrode. Let's do our E naught cell. Now, we know that E naught for the cathode will be 0, right? The hydrogen is, by definition, 0. So E naught anode will be the negative of the value here, because these are all reduction, right, potentials, so we want the oxidation. So we got to find aluminum. So if you look through here, right, look for the aluminum one. This is the hardest part, is finding the darn thing. Let's see, where is aluminum? There it is. Okay, can you see the aluminum +3 right there? +3 electrons going to aluminum solid. Well, we want the reverse of that, correct? So if we reverse the aluminum equation, boop, then we change the sign. See the negative 1.676 volts? We're gonna change the sign on that. So that'll be, oh, I fumbled it. Negative 1.676 volts with my ugly looking V there. So that we take the negative of that. So let's add those together. We got 2 electrons here and 3 electrons there. So we need to multiply this by 2 and this by 3. We look at the common multiple between them. All right, let's write down the overall equation. Hopefully you can already see with the shortcut When we add that plus that, it's going to be positive. This is going to react. We don't have to go through all this, but it never hurts. It's on the board. I got room. Let's do it. Now let's do the overall equation. So the electrons will cancel out. So we'll have 2 aluminums. 3 times 2 is 6 hydrogen ions. So 2 Al solid. Ooh, how do you spell aluminum wrong? Al. I just did it. That's it there. Plus 2 times 3 is 6H plus aqueous. This will be 1 molar. 6 electrons, that'll cancel out those 6 electrons there. That's the whole point. We're going to get 2 aluminum ions here, and that'll be 1 molar because we're at standard conditions. Let's see, 3 times 1 is 3 hydrogens. So here's our overall equation. So we're trying to see, is that spontaneous under standard conditions? Well, we know that E naught cell is the cathode plus the anode. And again, this is the style, that's the style I like to use. I don't like to use the one that has the negative sign there, which is catching steam, I guess. But I like you to realize, again, we're reversing this equation, right? This is the backwards reverse equation of what's on here, so we have to change the sign. All right, well, we know the cathode is 0 volts, plus this is going to be positive, right? 1.676 volts is positive 1.676 volts, right? It's just the reverse of the reduction half potential. Since that's positive, is greater than 0, this is spontaneous. And the reaction occurs. So good practice there, but really we could have done this almost in our head. We could have just went, all right, well, we know we're adding these two together. The cathode is 0. The anode will be the reverse of what's on here. So you look up aluminum and go, well, what's the reverse of negative 1.676? Positive 1.676. So you could have just done that in your head. Oh, but another reason I'm making you do this, we're going to have to do the half reactions to figure out the number of electrons that are transferring between them in order to do the next few sections. We're going to have to do some electron accounting, understanding we're going to have 6 electrons being transferred here. So we're going to give that a value called Z equals 6. We're going to need that number when we're dealing with equilibrium and non-standard conditions as well. So I'm just prepping you. If you do the shortcut every time, then you get stuck later because you lose track on how to do this. Not too bad. Metal activity series, right? Anything with a negative reduction potential would be a positive oxidation potential and would react with acid. Vice versa for something else. Not a big deal. Let's go to the next video.